Hi everybody, how are you this day? Okay, so I hope you are all fine there. And this moment, I will be sharing to you about Newton's laws of motion. Now, what comes first into your mind when I say laws of motion? Have you encountered this lesson before? So I hope so because it's so easy for you to understand if you already have background on it. Okay, so let's start. In the early 1600s, the Italian astronomer Galileo Galilei suggested that once an object is in motion, no force is needed to keep it moving. Force is needed only to change the motion of an object. Galileo's ideas paved the way for Isaac Newton. Newton proposed the three basic laws of motion in the late 1600s. Now, what are those three laws of motion? Let's find out. The first law of motion restates Galileo's ideas about force and motion. Newton's first law of motion states that an object at rest will remain at rest, and an object moving at a constant velocity will continue moving at a constant velocity unless it is acted upon by an unbalanced force. If an object is not moving, it will not move until a force acts on it. Like for example, clothes on the floor of your room will stay there unless you pick them up, right? Of course. If an object is already moving, it will continue to move at a constant velocity until a force acts to change either its speed or direction. For example, a tennis ball flies through the air once you hit it with a racket. If you are going to hit the ball with a racket, it will fly. If your friend doesn't hit the ball back, the forces of gravity and friction will eventually stop the ball. On Earth, gravity and friction are unbalanced forces that often change an object's motion. Now, finally, the first law of motion is the law of inertia. Whether an object is moving or not, it resists any change to its motion. Galileo's concept of the resistance to a change in motion is called inertia. Inertia is the tendency of an object to resist a change in motion. Again, what is Newton's first law of motion? That is the law of inertia. Inertia explains many common events, such as why you move forward in your seat when a car stops suddenly. When a car stops, inertia keeps you moving forward. A force such as that pull of a seat belt is required to change your motion. That's why people are advised to wear seat belts when they travel. Some objects have more inertia than other objects. For example, suppose you needed to move an empty aquarium and an aquarium full of water. Now, obviously the full aquarium is harder to move than the empty one because it has more mass. Of course, it's very heavy. The one with the water is heavier than that of the empty one, right? The greater the mass of an object, the greater its inertia and the greater the force required to change its motion. The full aquarium is more difficult to move because it has more inertia than the empty aquarium. So which one has greater inertia? The one with the greater inertia is the aquarium with water. Okay, now let's move on to the second law of motion. Suppose you are babysitting two children who love wagon rides. Their favorite part is when you accelerate quickly. When you get tired and sit in a wagon, one of the children pulls you. He soon finds he cannot accelerate the wagon nearly as fast as you can. How is the wagon's acceleration related to the force pulling it? How is the acceleration related to the wagon's mass? According to Newton's second law of motion, acceleration depends on the object's mass and on the net force acting on the object. This relationship can be written as an equation. Acceleration is equal to the net force over the mass. Acceleration is measured in meters per second, and mass is measured in kilograms. Now, according to Newton's second law of motion, force is measured in kilograms times meters per second. The short for this unit of force is the Newton. Recall that a Newton is the metric unit of force. You can think of 1 Newton as the force required to give a 1 kilogram mass and acceleration of 1 meter per second squared. Now let's have here a sample problem. A speedboat pulls a 55 kilogram water skier. The force causes the skier to accelerate at 2.0 meter per second squared. Now calculate the net force that causes this acceleration. What information are you given in this problem? Of course, the first one we have here the mass of the water skier, that's 55 kilograms. Acceleration of the water skier, that is 2.0 meter per second squared. What quantity are you trying to calculate? Of course, we have here the net force. And what formula will you use? Okay, so of course, acceleration is equal to the net force divided by the mass, or net force is equal to mass times acceleration. So now let's perform the calculation. We have the net force is equal to m times a. Okay, so now F is equal to, m is 55 kilograms and a is 2.0 meter per second squared. So now what are we going to do with that? We will multiply 55 times 2.0, and that is 110 kilograms meter per second squared, or 110 Newton. That is the answer. Now we have here changes in force and mass. How can you increase the acceleration of the wagon? Look again at the equation. One way to increase acceleration is by changing the force. If the mass is constant, acceleration and force change in the same way. So it increases the acceleration of the wagon. You can increase the force used to pull it. Another way to increase acceleration is to change the mass. According to the equation, acceleration and mass change in opposite ways. If the force is constant, an increase in mass causes a decrease in acceleration. The opposite is also true. A decrease in mass causes an increase in acceleration with a constant force. To increase the acceleration of the wagon, you can decrease its mass so that it will not be very heavy. So instead of you, the children should ride the wagon. It is to accelerate the wagon. So that is to increase the acceleration of the wagon. Now let's move on to the third law of motion. Newton proposed that whenever one object exerts force on the second object, the second object will exert a force back on the first object. The force exerted by the second object is equal in strength and opposite in direction to the first force. Like if I'm going to push it here, this one also will push like that, and they are equal in strength, but they are in opposite direction. Think of one force as the action and the other force as the reaction. So now let's think of it as the action, and this is the reaction. This is the action and then the reaction. Newton's third law of motion states that if one object exerts a force on another object, then the second object exerts a force of equal strength in the opposite direction on the first object. Another way to state Newton's third law is that for every action there is an equal but opposite reaction. Okay? That is action-reaction pairs. You're probably familiar with many examples of Newton's third law. Like pairs of action and reaction forces are all around you. Of course, we can encounter a lot of situations like that. When you jump, when you jump, you push the ground with your feet. This is the action force. The ground pushes back on your feet with an equal and opposite force. That is the reaction force. You move upward when you jump because the ground is pushing you. Okay, now let's have here detecting motion. Can you always detect motion when paired forces are in action? Is there a motion here? The answer is no. For example, when the Earth's gravity pulls on an object, you cannot detect Earth's equal and opposite reaction. Earlier, you learned that if two equal forces act in opposite directions on an object, the forces are balanced. Because the two forces add up to zero, they cancel each other out and produce no change in motion. Why then don't the action and reaction force in Newton's third law of motion cancel out as well? After all, they are equal and opposite. Okay, so that's all for the three laws of motion of Isaac Newton, and I hope that you learned something. Thank you so much for listening, and goodbye, everyone. See you.